Prior to this screencast, we have been focusing on input-output rules and features of input-output rules, and specifically looking at a lot of applications with respect to those input-output rules. For example, we looked at the relationship R equals 100 minus 14x, where x is the number of running shorts purchased and R was the amount of money left on a gift card. Though we've not discussed this yet, this relationship is what we call a linear relationship between x and R. There are lots of other types of applications where the relationship is not linear. For example, h, the height of a baseball, might be measured by negative 16t squared plus 95t plus 3, where t is the number of seconds after the baseball was hit. Notice with this particular input-output rule, there is an exponent on the input variable t. This relationship between the height of a baseball h, t seconds after it was hit, cannot be represented by a linear rule like this. It needs a rule like this that has an exponent of 2 on the input variable t. So what we will do in this section is make sure that you know what exponents are and how they're used and why. But you're going to notice the main objective here is for computational fluency. So we are going to be looking at a variety of exponent laws in this screencast, and you'll see it's not applied. So this is very computational. Make sure you practice these skills in order to develop them on your own. First, we start with some multiplicative notation. So if x and y are each variable quantities, what does xy mean? So if somebody writes xy on the paper, what does that mean under the assumption that x is a variable quantity and y is a variable quantity? When we put things together in mathematics with no symbol in between them, that means that we're assuming there is multiplication between them. So when we write xy, that means exactly x times y. People just write this for efficiency. There's one less keystroke you have to do here. So then if you were to look at the expression 5x, what operation exists between the 5 and the x? Well, this too, since we collapse the 5 and the x together, 5x means 5 times x. We just don't put the multiplication symbol of times in there. So 5x means 5 times x. This then brings us to exponents. Y to the third power. The use of exponents is part of our multiplicative notation in mathematics. So when people write y cubed, that means you're multiplying 3 y's, y times y times y. It's just a more efficient way. I'd rather write this, which is 2 characters, instead of 1, 2, 3, 4, 5 characters over here. Let's look at a formal definition and some terminology. The expression x to the n is in what we call exponential form. Now, whatever the number is that you're raising to the power, we call that the base of the exponential form. And that number in the superscript position is called the exponent. Sometimes you'll hear the exponent referenced as the power. Also, sometimes people will use power to represent this whole term itself. But we're going to refer to this number here as the base and this here as the exponent. So what is meant when someone writes this expression, x to the nth power? This represents multiplying n x's. So you've got x times however large n is, that's how many x's you need. So you need n of those. So for example, if you had 2 to the 5th power, that would mean you've got 2 times 2 times 2 times 2 times 2. You got the product of 5 2's. Now, there's some terminology that often goes along with this. If you have a second power, for example, x squared, people use, notice I just used it, people use the word squared to represent the second power. You could say x to the second power, or you could say x squared. If you have an exponent of 3, you could say x to the third power, or there's a special name for that one. We say x cubed. And in general, although there are some other names, in general, whenever n is greater than or equal to 4, so if you had x to the 4, this or this, we typically aren't going to use a special name for those. We're just going to read this one as x to the 4th power, this one is x to the 5th power, this one is x to the 6th power. We'll start to develop our computational fluency with exponential forms by first looking at expanding and contracting them. Let's write each of these expressions in exponential form. Again, what does it mean when I put -6 up against p, up against q, 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 r, and r? Again, this means we've got a product here, right? People just don't write in these little dots. Right? So we've got a product of all these things, and we want to write this in exponential form. Well, there's only one -6 factor, so I'm just going to write that. There's only one p factor, but then there's 3 q factors. So instead of writing q times q times q, it's simpler to write q to the third power. Instead of writing r times r, people would typically write r to the second power, or r squared. This is the exponential form of this expression. When you write something in exponential form, you are contracting it. Let's do it with this one over here as well. So the factors we've got here are 5. We've got AB as its own factor and AB as its own factor. Notice there's a repeated factor of AB. So instead of writing the AB twice, we can write this as 5 times AB, that quantity, to the second power. This is the contraction of this expression. This is its exponential form. Some of you may know some exponent laws on how to rewrite that. That's what's coming up soon. We also want to be able to go the other way. We want to take exponential forms and be able to write them in expanded form, essentially like this. And you're going to see the reason for doing that is the development of the exponent laws. How could you rewrite this without exponents? Well, we have a factor of 7. X squared means we have 2x factors, and y cubed means we have 3y factors. So 7x squared y cubed is the same thing as 7 times x times x times y times y times y. Now you might be saying, why did you make it more complicated? If I was typing this, this is faster to type than, say, this is. Again, the reason that we are writing it in expanded form is to develop the exponent laws. I want you to know where the exponent laws come from rather than me just telling you what they are. Let's expand one more here. We've got, in this case, 2x over y, that thing to the third power. So we got a fraction raised to the third power. So what is the base in this scenario? Well, technically, the fraction is the base because that whole fraction is being raised to the third power. So that means we are multiplying 3 of those fractions. We've got 2x over y times 2x over y times 2x over y. And again, we're just trying to write this in expanded form for reasons coming soon. We have one more technicality we need to look at before we start to develop the exponent laws. Does this expression represent a negative number? I know how many people read this, including me, but does it represent a negative number? So think about that for a moment. If x were 4, then if you plug 4 in for x, you get the number -4. If x were -4, you plug that in and you'd get this. But the opposite of -4 is +4. So this expression can represent either a negative number or a positive number. So very often, though, people read this as -x, but it does not mean the result is negative when you plug in a number for x. So in reality, this sign represents the word opposite. So when we often say -x here, what we really mean is the opposite of x. So for example, if x is 5, when you plug 5 in for x here, you'd get the opposite of 5, which would be -5. If you were to plug in -5 for x, then this expression would be the opposite of -5, which would give you +5. So you may be asking yourself, why am I even pointing this out? Well, it plays a big role in your understanding of the difference between these two expressions here. So according to my calculator, which you can see over here, this expression is +9. This expression is -9. And the whole question is why? And understanding this idea here plays a very big role in understanding why these two are different. Of course, this one is positive, this one is negative. And the reason is because the opposite sign, saying the opposite of x, is the same thing as saying x times -1. To get the opposite of a number, you multiply it by -1. If you had 7 and you wanted its additive opposite, you'd multiply by -1, because 7 times -1 is -7. If you had -20 and you wanted its opposite, you'd multiply by -1, because -20 times -1 is +20. So the opposite of x is precisely x times -1. This idea here explains why this particular expression is negative. It's because this is actually an opposite sign. This is basically saying, what's the opposite of 3 squared? 3 squared, of course, is 9, and then the opposite of 9 is negative 9. Whereas this one over here means that you're multiplying two of these numbers. So you've got negative 3 times, again, negative 3, if we were to expand it. And negative 3 times negative 3 is positive 9. So understanding this plays a key role in why this expression right here is positive 9 and this expression is negative 9. Now, I'll also explain in a little while how by the order of operations, this also would have to be negative 9. Because by definition here, this should be the same thing as negative 1 times 3 squared. And if you, of course, already know the order of operations, which is a prerequisite to this course, you know you do the exponentiation before you do the multiplication. So this would be negative 1 times 3 squared is 9, and negative 1 times 9 is negative 9. So there's multiple ways to think about why this is negative 9, yet this is actually positive 9. And the reason that I'm pointing this out is because you need to know what you're trying to get. If you plug this in your calculator and you want the square of negative 3, you've got to plug that in. This is not the square of negative 3. This is the opposite of the square of 3. Whereas this one is the square of negative 3. So you have to be careful with what you type into your calculator. We are now ready to develop some exponent laws.